Good afternoon, everybody. Thank you very much for coming along for the seminar today. We have a big treat for us today. Murad Tayebjee is giving a seminar on multiple exciton generation, which will be really interesting to hear about. Murad did his first degree at Sydney University and stayed there to carry on doing his PhD, which he finished in 2012. He's working on the thermodynamics of third generation photovoltaic devices with Tim Schmidt, who's up the back there. Then Murad came over to UNSW to carry on a arena fellowship, working on Singlet Fission, which is closely related to multiple exciton generation, as I'm sure we'll hear in the talk. And is also working on the hot carrier cell project at the moment, before he leaves in the very near future, just over a month, I think.
Yep.
Yeah.
Yep.
For to go to Cambridge University, where he's starting a Marie Curie fellowship, which I'm sure will be a very exciting first time you're working outside Sydney.
Yep.
Yeah. So okay. So thank you, Murad. We look forward to hearing about.
Thanks very much, Gavin. Today I'm going to talk to you about some of the work I've been doing over the last 3 years. I've been at UNSW looking at a process called Singlet Fission. So the first question is, what is Singlet Fission? I realise we've got a bit of a mixed audience, so I'll go through some of the details of what this process is. But before we get started, we need to take a look at the molecular states that are involved in Singlet Fission, because I know a lot of the people in the audience work largely with bulk semiconductors. So I'm going to be talking about 3 states very often in this talk. The S0 state, which is the ground state here, where you have two electrons in the highest occupied molecular orbital, and their spins are antiparallel. The S1 state, which has 1 electron in the LUMO and 1 electron in the HOMO, and again the spins are antiparallel. And the triplet state here, which is the T1 state, which has electrons in the same molecular orbitals as the S1 state, but the spins are aligned. And it's called a triplet state because there are 3 of them. So you can have the spins precessing around the 3 axes of the molecule, the X, the Y, and the Z axes of the molecule. So this is a molecular orbital diagram, but for the rest of this talk, I'm going to be using a state diagram that looks a little bit more like this. So you have the S0 state, which is the ground state, which is the lowest in energy. Then you have the T1 state, which is the next one up, and the S1 state, which is the highest one here. So in the Singlet Fission process, what we have is a photon will excite one molecule from the S0 state to the S1 state. And in this process, we're actually going to generate 2 excitons. And the nice thing about this is the S1 state will not decay down to the T1 state, because that's a spin-forbidden process. And that's called intersystem crossing, and it's very slow in the molecules of interest for this talk. But what can happen is something called Singlet Fission, where you take the S1 state and you produce 2 triplet states. Now this means that you need 2 molecules next to each other. So one's in the ground state, one's in the excited state, and then you undergo Singlet Fission and you produce 2 triplet excitons. Now the reason this is a rather fast process, it can happen on the order of about 100 femtoseconds, is because it's a spin-allowed process. So you can imagine that the 2 triplet states have spins that are aligned anti-parallel, so there's an overall singlet configuration, and this means that this process can occur in a spin-allowed way. And then the nice thing about this idea is that these excitons are also long-lived for the same reason we didn't have intersystem crossing from the S1 state to the T1 state. So from the T1 state to the S0 state, it's again a spin-forbidden process for that decay, so these triplet excitons will live for a long time. So overall, we've produced 2 excitons from the absorption of 1 photon. Now there are a fair few molecular systems, and if the energetics work out, we can actually get the reverse process, which is called triplet annihilation, where 2 triplets come together to produce a singlet exciton. Now the Singlet Fission process has been shown to work in many molecules, and this is from a review article from 2010, and these were the molecules being looked at then. This is the number of molecules that are being looked at has actually increased a fair bit. But in this talk, we're going to just stick with 2 of them. We're going to look at tetracene, which is number 2 on that diagram, and pentacene, which is number 3 there. And we're going to look at slightly different variations of this molecule with solubilizing units, but these are the main absorbing units, or the main chromophores that I'm going to be talking about throughout this talk. So for the rest of this talk, I'm going to go through basically what I did over the last 3 years, and it was approximately over a year per topic here. So first I'm going to take a look at the theoretical potential of Singlet Fission technologies. And then I'm going to look at the effect of chromophore coupling on the rate of singlet fission, so how close these molecules are together and how that affects the rate of singlet fission. And finally, what I've been doing over the last about 12 months is observing the intermediate state that occurs in the singlet fission process. And we did that using magnetic resonance spectroscopy. So let's take first of all a look at what singlet fission can be, what the limiting efficiencies of a singlet fission device would be, a solar cell. Now, the reason a singlet fission device will be more efficient than, say, the Shockley-Queisser limit is because we have two absorbing thresholds. So we have an absorbing threshold that we usually have for an inorganic cell from the valence band to the conduction band, as you would expect for, say, a silicon device. I'm just going to call that energy level ER for absorbing a red photon. And we have another threshold up here that I'm going to call EB for absorbing a blue photon, where the multiple exciton generation or singlet fission process can occur. Now, the theoretical outline I'm going to give here is completely general to any multiple exciton generation process, not just singlet fission. So in, say, a bulk inorganic like silicon, we call this impact ionization. In a low-dimensional inorganic like lead selenide quantum dots, we call it multiple exciton generation or carrier multiplication. These are all the same sort of things in a detailed balance approach to limiting efficiencies. Okay, so we can generate current in this device via two mechanisms. The first is the regular mechanism where you absorb a red photon. You go from you excite an electron from the valence band to the conduction band, create an electron and hole pair on an exciton, and then you can extract the electron and hole at some voltage. But in a carrier multiplication cell, you have another mechanism of generating current where you can excite an electron from the valence band to this exciton fission level, and then this will actually produce two electron hole pairs, and then you can extract this as extra current, and this will mean that you can have a larger current from your exciton fission capable device. So prior to the work that I did in my PhD, there was an assumption in the literature that the energetics of the system would have to have the level EB at least 2 times ER, and that's just to conserve energy. But at any given temperature, we can consider that fission may actually be an endothermic process. So if we consider the overall enthalpy of the fission process, we have the final energy is 2 times ER minus EB. But we know that under steady state conditions, the free energy change is going to be 0. So we can also say from this that the change in enthalpy will be equal to the change in entropy multiplied by the temperature of the system. And by including this into our calculation, we can actually say that EB on ER can be less than 2 for any temperature greater than 0. Now, there's no magic here. This is just allowing for an endothermic process to occur. But prior to this work, no one really included it in their calculations. And it does make a pretty significant difference to the limiting efficiency of these devices. So those of you who work with real solar cells here are going to look at these numbers and say, yeah, that's not realistic. And I completely agree. It's not realistic. These are magic absorbers that have unit absorptivity. There's infinite carrier mobility and no non-radiative recombination. So we're looking at a real theoretical thermodynamic limit of these sorts of systems. So prior to our work, only exothermic and isoenergetic fission was looked at. And so on the y-axis here, we have the energy of the lower threshold. So this is like the band gap of the device. And on the x-axis here, we have the ratio of that higher energy to the lower energy threshold. So prior to our work, it was only considered that this ratio could only be 2 because they're conserving enthalpy, but not the total free energy. And you get a limiting efficiency of something like 41.9%. However, if you include endothermic fission in this process, you can actually increase this limiting efficiency from 41.9% to 45.9%. This isn't entirely theoretical because singlet fission has been shown to occur endothermically in a system in tetracene, in that molecule I showed you on a slide earlier. So if we include endothermic fission, it is actually reasonable to do so because we may be able to generate a device that can generate 2 excitons in an endothermic manner. And if you want to compare the limiting efficiency of a singlet fission cell to other third generation technologies, we've got this over here. So on the x-axis, we've got the band gap of the device. On the y-axis, we've got the limiting efficiency. Again, these are going to have some crazy numbers to real device makers over here, but these are the limiting efficiencies of the device. We've got the Shockley-Queisser limit, which most of you would know about here in black. And then we're following this 2M curve where we generate 2 excitons from the absorption of 1 photon, and we can get to a limiting efficiency of 45.9% here. IB is for an intermediate band solar cell. UC, there's a cell that's augmented by up conversion, and DC is a cell that's augmented by down conversion. So this is how a singlet fission device compares to the other third generation technologies, with the notable exception of hot carrier cells, which can't be treated in such a simple, detailed, balanced manner. It's also interesting that the maximum here is pretty close to the silicon band gap. And that got us to thinking, what if we put a singlet fission capable material on top of silicon? That way we don't have to reinvent the wheel, because silicon's already a very mature technology. It turns out we didn't have that idea first. It was actually proposed by Dexter in 1979, somewhat before I was born. But the idea is that, okay, what if we can enhance an existing technology, something like a rear-contacted silicon cell? So I reperformed these calculations, but this time I used more realistic values for the tetracene, so for the singlet fission layer, but I kept the unrealistic values for the inorganic layer. So the idea of these calculations is to show how much we could augment an ideal device with a singlet fission layer that's put on top of the device. So something like an organic material on top of an inorganic material, and there's got to be some sort of charge separation mechanism at this interface. Now, I completely parametrically included this charge separation mechanism to be, you have to give up some sort of energy to separate a triplet exciton, and they're given as different energy sacrifices of 0.1 all the way to 0.5 eV. And for reasonable energy sacrifices, we can still exceed the Shockley-Queisser limit. So this suggests that a tetracene on silicon cell may actually be able to exceed the Shockley-Queisser limit by augmenting the current of the device. We have some collaborators in Germany that tried to make this device, and they made a working device with a tetracene absorber on the device. It just acted as a filter. So unfortunately, whilst we can theoretically circumvent the Shockley-Queisser limit, currently our collaborators and the groups at MIT and Cambridge also working on this, no one's been able to actually separate a triplet exciton at the silicon interface. This doesn't mean that the singlet fission work is completely useless, because people have been able to inject triplets into, say, a lead selenide or a lead sulfide quantum dot, or even into a C60 device. So you could have a completely organic cell that is singlet fission capable, and they've shown EQEs of above 100%. But still, if we're going to go with the original idea of trying to augment a mature technology, then we really need to understand more about what happens at the organic-inorganic interface, and that's going to be a lot of future work, and there's going to be other molecules that are used, but currently that's the state of the technology. Okay, so now that's the theoretical portion of the talk. We're going to move to some of the actual experiments that I did. So I looked at, in the second year of this fellowship, I was looking at the rate of singlet fission in some nanoparticles of TIPS pentacene. So you remember that pentacene is this molecule here, and the TIPS groups are these groups here, which don't really change the absorption properties so much. They're more there to make them a soluble molecule. Now the first question is, why would you look at nanoparticles? The answer is it's a nice system to study. Basically, they're in the solution state, so some of the spectroscopy becomes a little bit easier. I have some control over the size of these molecules, and I also have some control over the morphology. So what I was interested in is how these molecules are oriented in space, and how does that affect the rate of singlet fission? We use TIPS pentacene because we know in thin films, TIPS pentacene gives you a fission yield of 200%, and fission proceeds on the order of 100 femtoseconds. So we know this is a very good fission material, and I wanted to see whether the morphology affects that rate of fission. Another reason you'd want to use nanoparticles is that, in principle, we could make a device by spin coating from a water solution. So there is a group at, I think, Karlsruhe Institute of Technology that is now looking at bulk heterojunctions that are deposited from water. So they're really making a green process to create organic solar cells. Currently, most organic solar cells are made from halogenated solvents, which are a little bit, they're not so friendly to the environment. So this is another reason that we used water suspensions of nanoparticles. So And the final reason is that we're able to mix nanoparticles together. So on the right-hand side here, I have a tetracene nanoparticles. On the left-hand side, I've got these Bipentacenes nanoparticles. And in between, I've got mixtures of these particles. And so these are mixed nanoparticles with tetracene next to pentacene in one particle. And what I've been able to do there is broaden the spectrum over which the singlet fission process will occur. So we're just going to focus on the results from the TIPS pentacene work. So on the left-hand side here, I've got the AFM of these nanoparticles. But in general, as a matter of course, we use DLS to show the size of these particles because the DLS match the AFM results and AFM takes a lot longer. DLS is a much more plug-and-play sort of technique. We're able to create these particles in a pretty reproducible way. And we're also able to control the morphology in a pretty reproducible way. So by controlling the solvents that we use to make these particles from, we can either create only type 1 particles, where as we age these particles over the course of 6 months, we get very little degradation, and there's no peak that occurs around 700 nanometers. But if I change the solvent system slightly, I'm able to get a peak to grow in around 710 nanometers, and that grows in over the order of months. And what that peak means is that you've actually got two pentacene molecules very close to each other, and they're coupling. So you get another absorptive peak that comes up around here, and that actually matches the thin film spectrum a lot more closely. So by comparing the singlet fission mechanism in both of these nanoparticles, we're able to look at the effect of chromophore coupling on the rate of singlet fission. So just to give you an idea, so a physical picture of what's going on here. So the type 2 particles, we have that extra absorption around 700 nanometers. You have your pentacene molecules are this nice brickwork structure, and there's very high coupling between the molecules. In the type 1, we're more amorphous. Now, from the thin film results, we know that fission occurs extremely quickly. So I would have expected that the type 2 molecules will give you very, very rapid fission, and the type 1 molecules will have some sort of slowed fission rate. So we then checked whether this was the case, but we found actually the opposite. So this is transient absorption data that I collected from, with collaborators from the University of Melbourne. And on the left-hand side here, we've got type 1 particles, and you can see that we have this absorptive transition that's out here for the triplet absorption, and we've also got a singlet absorption transition here, and we've got the bleach of the initial signal over here. In the type 1 particles, the bleach grows in over time, and that should happen if you have a singlet fission process. And the singlet absorption sort of dies off, and the triplet absorption grows in. So this is really indicative of a singlet fission process. And that's occurring in the amorphous particles, in the type 1 particles. And it sort of occurs with a lifetime of 1 picosecond. That's reasonable considering the thin film singlet fission process occurs with a lifetime of 0.1 picosecond. So we've slowed it down by reducing the coupling, and that's what I expected. What I didn't expect is that in the type 2 particles, we didn't produce any triplets at all. So for some reason, the singlet fission process appeared to be shut off. There may be a slight shoulder here of absorption for the triplet, but it's not clear that we produced any triplets at all. And in order to understand this, we went to a different spectroscopic technique called Ultrafast polarization and anisotropy. So I'll just go into this in some quick detail. It's a fairly complex experiment. But basically, we have a femtosecond laser, and we split the beams into an excitation beam, which is given here in green, and a gate beam that's in red. So the excitation beam passes through a polarizer and a half-wave plate that allows us to choose the polarization with which we excite the sample. And then we take the photoluminescence, given here in orange, and we focus that onto a nonlinear crystal. Now, while all of this is happening, we have a gate beam, which is passing through some optics and is also focused on the same nonlinear crystal. We then take the upconverter, the frequency summed light, and pass that through a monochromator and onto a photomultiplier tube, and that's how we detect the fluorescence. Now, the way the nonlinear crystal works is that you need the polarization of the gate beam to be the same as the polarization of the photoluminescence. So we can actually generate a parallel polarization experiment by hitting the sample with, say, vertically polarized light and having a gate beam with vertically polarized light, and a perpendicular orientation of the polarizations by rotating the excitation beam so that we have horizontally polarized light, and we still have a vertically polarized light for the gate beam. And you can imagine that as you excite a sample with vertically polarized light, it will immediately emit with vertically polarized light. But as the sample sort of tumbles, that polarization and anisotropy will get scrambled. And so that's what we're looking at in this particular experiment. So I'll show you some data, and I think this will become a little bit more clear. I'll show you, what will actually cause the anisotropy to decay. So what brings the parallel orientation down, so the parallel orientation of this decay closer to the perpendicular orientation, what dephases the polarization anisotropy? So we expect there to be no decay in this anisotropy in the type 2 regions, and that's because all of these molecules are aligned, so we expect the polarization to be the same in all of these type 2 regions. And we expect there to be no anisotropy decay in excitonic traps because they're going to be the polarization stuck on one molecule. Now, I should note here that this is an ultra-fast experiment, so we're looking at polarization decay on the order of picoseconds. These nanoparticles are tumbling on the order of hundreds of nanoseconds, so that's not going to be the mechanism for polarization anisotropy decay. How it will actually decay is when excitons migrate within amorphous regions, so when an exciton jumps from molecule to molecule, and that will scramble the polarization, or when excitons migrate across grain boundaries, that will also scramble the polarization. So if we look at the results of this work, in this inset here you have the different absorption spectra of 3 batches of nanoparticles. This one is our type 2 nanoparticle. It's very highly coupled chromophores. And we can see that for the polarization independent, or the magic angle result, we have a very, very fast initial decay. And that's probably because we do have some singlet fission in these highly coupled nanoparticles. But then there's also a very, very long tail on this decay. Now, if we match that long tail to the anisotropy, we can see that there's also a very, very long anisotropy on these type 2 nanoparticles. So what this actually is we have exciton traps that are in these type 2 nanoparticles. And the reason they exist is because, if you remember for a few slides back, the way I made type 2 particles is by aging them over the course of months. So this slow crystallization process actually generates a very trappy material that, while some chromophores stay very coupled and you have some chromophores giving you very fast singlet fission, the majority of them appear to just generate trap states. And actually, this makes the singlet fission process very inefficient. So that's not what I expected. Conversely, if you look at the amorphous material, A and B here, it's a much less trappy material. So it might actually be better if you're going to deposit from a nanoparticle solution to use the amorphous TIPS-pentacene rather than the highly coupled type 2 TIPS-pentacene. So the main takeaway the main thing I want you to take away from this section is that there are 2 things that you need to take into account. It's first short range order that plays a role in singlet fission. So if you have highly coupled chromophores, you'll get a rapid singlet fission rate. But the long range order also seems to play a large role. So you have to consider both of these if you're going to try and make a singlet fission capable device. In the next part of my talk, I'm going to look at singlet fission in bipentacenes, where we're only going to look at short range order. So we're going to get rid of one of those variables. So at a conference I went to, I met with a student who actually had already made these molecules, so that was quite nice. So he's made pentacene dimers. So these are the 2 absorbing units, and they're covalently bound. So now we can get singlet fission to occur in solution in an isolated molecule. You don't have to have 2 molecules stuck together. You just have these floating around in solution. And he's already shown that this has undergone fission. I should say that the student I was working with is Sam Sanders from Columbia University. So just to give you the nomenclature that I'm going to use for the rest of this talk, BP stands for bipentacenes, and BP0, BP1, and BP2 stand for the number of phenyl rings that are between the 2 pentacene molecules. So BP0 has no phenyl rings, BP2 has 2 phenyl rings, and obviously as you increase the number of phenyl rings, you reduce the coupling between the 2 pentacene units in this dimer. Okay, so the question that we were going to answer was something that they brought up in their paper. In their original publication, they presented TA data showing that they could generate triplets from singlet fission, But the dynamics of the triplets that are generated using the Singlet Fission process was different to the dynamics of triplets that are just generated via sensitization. So sensitization is where you have these two molecules, you have a dimer floating around in solution, but you excite a different molecule that can donate a triplet to that dimer. So you excite that molecule, it passes the triplet energy to the dimer, and then you look at how the triplet decays over time. And they showed that if you sensitize the molecule, the triplet will decay on the order of 18 microseconds. But if you generate your triplets via Singlet Fission, these triplets decay on the order of 450 picoseconds. So there's something different about triplets generated by fission versus triplets that are just donated by a different molecule. So the starkest contrast was in BP0, but in BP2, you can actually see that fission, again, generates triplets that decay quickly, but there's also a long tail suggesting that there are some triplets that decay at this slower rate. They had some ideas of why this might be, but when we were talking, we didn't really understand what the reason was for these two different decay rates. It doesn't really make sense. So the one thing that we need to take into account is the experiment that they were doing. They were doing a transient absorption experiment, which is a pump probe experiment. So use an optical pump to pump from the S0 state to the S1. The system undergoes Singlet Fission, which is also can be thought of as internal conversion, and you produce two triplets. Now, if you consider that these two triplets are still really strongly coupled in a triplet pair state, and then you send in a probe pulse, and then you can take a look at how many triplets you've produced. The problem with transient absorption is that you can't tell the difference between two triplets that are really strongly coupled and two triplets that are not near each other and not coupled at all. I should make the disclaimer that there are groups around the world that say that you can see this, but it's only in very subtle changes in the transient absorption spectrum. It's quite difficult to tell whether your triplets are coupled or not. So to take a look at this in a bit more detail and to understand what's the difference between a Singlet Fission generated triplet and just free triplets, we put the entire system in a magnetic field. So since triplets have overall net spin, you can split the energy off the triplets in a magnetic field via Zeeman splitting. So we did an experiment that's transient EPR, which can sort of be also be thought of as a pump probe experiment, where you have an optical pump, a nanosecond pump that will pump from the S0 state to the S1. You undergo fission to this triplet pair state, and then in a magnetic field, these triplet pair states get split apart by the Zeeman effect. Now, the reason I've drawn 9 states there is that you have 3 triplets, right? So you've got 9 different configurations of a pair of triplets. 3 times 3 is 9. I should note that the probe here is a microwave. So you're not using an optical probe, you're using a microwave. This is a really small energetic difference. And by looking at the spectrum that you generate from this, you're able to see what the spin state is of these molecules. So unfortunately, the only way to understand this is to go into a little bit of maths, but I promise that this will be brief and relatively painless. And we have to consider the full spin Hamiltonian. Okay, let's break this up into the 3 terms. There's the Zeeman term, which I discussed earlier, which splits all your states in a magnetic field. You have a zero field splitting term, which, as the name suggests, is the splitting of your triplet states under zero field. Now, this splitting is really, really small. Usually, for most experiments, you assume triplets have the same energy. But in a EPR experiment, in a magnetic resonance experiment, this splitting actually matters. It's on the order of micro EV. And we also have a third term, which couples 2 triplets. Okay? So, a little bit more maths, but I'll try and do it pictorially. You have the zero field splitting. Like I said, that splits your states, your triplet states, the X, the Y, and the Z triplet in energy, and this is a really small splitting. If you apply a magnetic field, these states will split even further because of Zeeman splitting. But now, we're going to use a different basis. So at zero field, the spins are aligned with the axes of the molecule. At a high field, the spins become aligned with the applied magnetic field. So it's just a change of basis, and you have a perturbation of these states by the zero field states. It's probably easier if I just show you what a spectrum looks like. So if we have occupied the zero state, you can get absorption from the 0 to the plus state, and you get this red curve here. And if you've also occupied the 0 state, you can get emission from the 0 to the minus state, which is this blue curve here. So the EPR spectrum will look something like this for a triplet. What I want you to take away from this is that a triplet has spacing between these resonances of x, which is equal to d minus 3. So that spacing is important. OK, so now we've done the Zeeman term, and we've done the zero field splitting term. Let's include the interaction term. Again, this looks complicated, but there are only a couple of things you need to take away from this. So in the pair states, there are the 9 pair states I was telling you about. There's an overall singlet state that singlet fission will go to, because as I said earlier, singlet fission is a spin allowed process. You go from a singlet to an overall singlet, here. Then we have 3 triplets and 5 quintets. Now, these are the solutions to the Hamiltonian. All I want you to take away from this is that you initially fission into this singlet state, and as the XX, the YY, and the ZZ begins to dephase from one another, you pick up some quintet character. So because these terms are found in the quintet states as well, you can actually generate a triplet pair state with some quintet character. Now, if I put it all together, this is the entire Hamiltonian. Once again, what I want you to take away is that we're going to undergo singlet fission into the singlet state here. And as these states begin to dephase from one another, we produce some population in this quintet state here. This is all theory thus far. And this state has never actually been seen in a single molecule until the experiments that we performed. So again, using that spacing that I brought to your attention earlier, that's the spacing of x for the triplet and the spacing of x on 3 for the quintet. All right, that's enough theory. Let's look at the actual data. So on the y-axis here, we have the field that this system is under. On the x-axis, we have the time after a laser shot. And I've got the spectral slices at different times shown over here. So we have an initially generated state that looks like this, and we have a pair of absorptive and emissive peaks. And then at longer times, we have a pair of absorptive and emissive peaks that are separated by a wider field. And as it turns out, that separation is x and x on 3. So we're able to assign the spectrum pretty quickly. So the initial spectrum is this quintet state, because that's generated by the singlet fission process. And the final spectrum, just based on where their resonances are, could be due to 3 things. The first thing we considered is that it's the higher spin quintet states, the higher M sub s spin quintet states, but we're able to cancel those out because we expect that the quintet signature would die off over time, and it doesn't. Oh, sorry, would not die off over time, but it actually does die off over time, so that can be cancelled out. And we can also cancel out the idea that it's the triplet pair states, because that requires way too much spin orbit coupling. It's not realistic. So what we have assigned it to is the free triplets. So what we think is happening is you initially generate a quintet state, which is the triplet pair, and then through some sort of molecular reorientation, you produce 2 free triplets that are isolated on the pentacene molecules. So that's the physical picture you should take away from all this maths and spectra. But we needed to prove this, and the only way to do that is to perform a nutation experiment. So without going into the details of this, basically by looking at the Rabi frequency of each of these transitions, you're able to assign the spin multiplicity of these states. So from theory, we expect the ratio of the Rabi frequency of the quintet state to the triplet state to be the square root of 3, which is 1.73. And if our assignment was correct, we'd get 1.73, and we indeed get a number that's pretty close to that. So we're certain that we initially produce a triplet pair state, and that actually lives for the order of microseconds, and then through some sort of molecular reorientation, you get 2 free triplets. And this can be modeled dynamically using a really simple ODE. So it looks complicated, but just by using first order ordinary differential equations, we're able to reproduce. So this is a simulated spectrum, and that's the data. So it's pretty clear that we've got a picture of what's going on in BP3. So now we're going to move to BP2. So that was BP3 are 2 pentacene molecules separated by 3 phenyl rings, so they're quite far apart. We're now going to move them 1 phenyl ring closer and look at BP2. And initially and by a first cursory look, it looks exactly the same. You have some initial peaks that are separated by x and some outer peaks that are separated by x on 3. However, if you look a little bit more closely, that peak shifts very, very slightly, and we have a slight absorptive region here, which can't be explained by simply going from a quintet state to 2 free triplets. So instead, what we consider is that the free triplets are actually coupled in some sense. And this makes sense. So if you have an overall quintet state that then moves to 2 triplets that are isolated on the separate parts of the molecule, and they're still weakly coupled because you have a shorter biphenyl bridge instead of the triphenyl bridge in BP3. So this is evidence that we have the triplet pair state dissociates into 2 free triplets that still have some coupling. And in order to prove this, we again perform the same Rabi oscillation experiment. And we expect that because the final triplets are still coupled, we shouldn't get that same ratio of square root of 3. It should be something different. And without going into the complexity of this, it was different. So we suggested that this is actually what's happening. We initially produce a quintet, and then that later dissociates into 2 triplets that are still coupled. The final piece of evidence that this is the correct model comes from the temperature-dependent transient absorption. So I'm jumping back now to the transient absorption data. And as a function of temperature, we can see that the initial decay of the triplet state is very, very similar, and regardless of temperature, and that's due to the fission process. However, at longer times, these dissociated triplets, you actually get more dissociated triplets at higher temperature. And this suggests that the dissociation of the triplets is actually a thermally activated process. So the singlet fission process produces 2 triplets that are still strongly coupled. And whilst they're coupled, they actually decay back to the ground state more quickly. You need to then dissociate the triplet pair if they're going to be useful in a solar cell. So this is the overall model for these bipentacenes. The fission process produces triplet-triplet pair. You have to go over some energy barrier to dissociate these triplets. And whilst they remain in the pair state, remember that the reason singlet fission occurs is because it's a spin-allowed process. So the pair state has some singlet character, and that can decay back to the ground state quite rapidly. So if you want to get everything out of your singlet fission system, you not only need your system to be strongly enough coupled to make the singlet fission process occur, you need it weakly enough coupled that the triplets will dissociate, so you actually get 2 free excitons rather than 2 excitons stuck together. So that's something that's a little bit more subtle about the singlet fission process. We can drive it to be extremely fast on the order of 100 femtoseconds, but whether we can actually extract those triplets will depend on playing with the coupling between the two molecules involved in the process. The other conclusion here is that the transient absorption tells you a lot. It tells you how many triplets you have. It gives you a good idea of the yield, and it has a very high time resolution. However, in my opinion, it can't really tell you what the intermediate state looks like and whether your triplets are still coupled. So you need to use magnetic resonance techniques to actually see what's going on in the intermediate state. Okay, with that, I'm left to thank a lot of people over the last 3 years. First of all, from SPRI, I didn't mention some of the other projects I was working on. Some of the hot carrier stuff I was working with the third generation group led by Gavin and Santosh. Also some of the bulk heterojunction work, I was working with some of Ashraf's students. Some of the plasmonic work I've been working with Supriya, and some of the perovskite work I've been working with Armin and Ziv. In addition, I've done some upconversion EPR work, and I wanted to thank the guys at the Free University for their help on that. Our collaborators at the Helmholtz Zentrum for the tetracene on silicon devices. Ultrafast spectroscopy, so all the photoluminescence work was done in Tim's lab at the School of Chemistry, so just across the walkway there, with Rowan and Miroslav, who are no longer at UNSW. The transient absorption for the nanoparticles was done in collaboration with Ken Gigino's group at the University of Melbourne. And the bipentacene work, the design and synthesis of the molecules was done by the guys at Columbia University. The transient absorption was performed by Matt Sphere at Brookhaven, and the EPR was conducted in the School of Physics with Dane McCamey. And of course, none of this would be possible without people paying for it, so I'd like to thank these groups as well, particularly Arena for funding my salary over the past 3 years. And thank you all for listening.
Yes, we've got a fair bit of time for questions.
Thank you, Murad. That was very interesting. I'm not going to go anywhere near that last section, leave that as it is. But regarding the detailed balance modelling,
Yep.
so where you identified that you could have this process occurring for less than 2 times the energy, you saw that the limiting efficiency increased from 41 to 45%.
Yeah.
Is that under the assumption that all photons undergo this single?
So you have to get over, yes, it's 100% fission yield above that threshold. Yeah.
Okay. And so is that largely just impacting JSC, or?
Yes, it's largely impacting.
So is there a dependence on the fill factor as well, or?
So the fill factor doesn't come into it as much because we make all these detailed balance, sort of these unrealistic assumptions in the model, because it's a limiting efficiency model. So the fill factor doesn't really play a large role.
Okay, so it's just increasing the photocurrent generation.
Yep. Yep.
Yeah, very, very interesting talk, quite inspiring. Good results. I got a couple of questions. The first one is actually again hitting on the same point with having Singlet Fission with slightly less than twice the energy. Basically, you cool your absorber with that, which is very nice. Actually, also happens in solar cells, as Carl Burr has been shown some 30 years ago. But I'm wondering what the major effect is. It's not really. I mean, you always talk about efficiency, but what also should be talked about is power flux, because it can have very high efficiency, but especially with the detailed balance limits, but very, very low power flux, and that's not really what you want, because you want extra energy after all. So my question is what the major effect actually is apart from increasing efficiency. So do we increase actually power flux? So do we increase the oscillator strength of the triplet transition, basically from the singlet into a couple of triplets?
So you're augmenting the current. So you can consider this as a if you have an equivalent circuit sort of model, you can consider this as having 2 cells connected that are voltage matched, with the upper cell, the higher threshold cell, having a perfect step down converter. So you step down in voltage and you double the current. So yes, you are increasing the power flux because within the multiple exciton generation model, the equivalent circuit just it's basically having 2 cells, and that one cell you're doubling the current and halving the voltage, and then you voltage match those 2 cells.
So what I actually mean is the effect of having slightly less than, slightly less than twice the energy. Does that actually affect your current? Because you draw on KT basically, that's what you do.
Yes.
And that could actually mean that your oscillator strength goes down. That means your quantum mechanical sufficient probability in Fermi's golden rule goes down, because you have to rely on a photon detail.
So oscillator strength are you?
The oscillator strength of actually having a singlet going down to a triplet configuration while kicking up another triplet. So you get 2 triplets out of one singlet. That's what.
Sure. Yes. Okay. Sure.
So the oscillator strength from Fermi's golden rule of that would also depend on a thermal phonon coming along.
Yes.
Exactly at the right time.
Yes.
And
So
that is actually fairly. It's actually a relatively large time window, because with uncertainty principle you have relatively low energy.
So I can tell you the experimental result that sort of maybe puts this at rest. So in tetrazine, you have the S1 level at 2.3 eV, and the triplets are at about 1.25 eV. So the change in enthalpy is 0.3 eV, and the Singlet Fission process dominates the decay of the singlet state. Yeah, it's quite a lot. Now, there's a little bit of a lack of understanding about this, and maybe it comes to the multiple exciton state that you're going to, and maybe that's at a slightly higher energy or something like that. But we do know that we get very high fission yields in an endothermic system. So I don't think it's unrealistic from the experimental work.
No, I don't doubt that. I'm just wondering what the effect is, to have slightly less than twice the triplet energy. So what the effect would be in terms of transition probability,
Yeah, of course. Yeah, so it would reduce the transition. Yes, yeah. So it would reduce the transition probability. So yeah, so an exothermic process would be, of course, more probable than an endothermic process, but it still can compete very favorably with the other decay channels of the singlet state. And that's really what matters. It's how it competes with that decay channel, with the other decay channels of the singlet state.
Well, can we take another question?
So I have a question about your quintets.
Yeah.
Okay, so you did this experiment cold, right? Like nitrogen cold or something? Or helium cold?
Yeah, I did a few temperatures. But
okay, so they're frozen, right?
Yeah.
As in the solution is frozen.
Yeah, it's glass.
So you say that the mechanism where you switch from quintet state to two separate triplet states is because the molecule is somehow reoriented itself?
Yes.
Is that a realistic thing in a frozen solution?
Yes.
And so what time scale would that be on? Because it would change for a
microseconds, according to the data.
So it would change for a BP0, BP1, BP2, right? As that linker chain is longer or
Yeah. So
or
it's
less
slower in BP3 and it's faster in Well, yeah. So they stay more coupled in BP2 than in BP3. So I think the best way to understand that is to look at the TA and see that there is definitely a thermal activation for that separation. And the fact that there's a thermal activation suggests that there's a geometry reorganization. And then there necessarily has to be one, because if the lowest energy state is already the triplet-triplet pair, then you need a reorganization of the nuclear coordinates in order to isolate the triplets. So the data suggests that there has to be some sort of reorganization.
Can you model what that is?
I can't, but hopefully our collaborators can. So they are guessing that it's the Arrow bridge that's rotating, because the potential energy surface for that rotation is quite shallow.
Because that would change what your nutation frequency is.
What, the rotation of the molecule?
No, so the rotation of the model affects what your coupling is.
Yes.
Right. So not only does it separate them out, but also it affects what that coupling is, and so that would possibly explain why you don't get that root 3, you get like 1.
Exactly. Yeah. That's So we thought there was some weak coupling there in BP2. Yeah.
Coming from a silicon background, I'm just wondering if you could comment further on the future of this work for this sort of absorption on like a silicon set.
So my feeling is that tetracene has been studied since the 60s, and it's the worst model system that exists because there's so many different things going on. Triplet annihilation and all this stuff is going on. I think that if silicon's going to be augmented, it's going to have to be a different molecule that's used. Perhaps a TIPS tetracene or something like this, something's built on the tetracene chromophore. But I also think that unless we understand how triplets are injected into silicon, there's got to be some really fundamental work done first before we can augment the cell, and that is being done already. So there are two ways we can get the triplet energy into silicon. One is what I drew in that in the diagram where you have the triplet actually separating, and you use the tetracene as the p-type material. But another way it could be to actually just take the full exciton energy in, and for that to happen, you'd have to take the triplet and then actually radiate it into the silicon cell, and perhaps that's the most promising thing. There are some pieces of work on nanoparticles that show that could be done, but then we're adding another layer. And the nice idea was that we don't want to change silicon too much because it already works very well. But yeah, I do see a future for it. And I think, in my opinion, the future is, the holy grail is making silicon better, because I don't think we can beat you guys. Yeah.
Perhaps a remark on the silicon Singlet Fission and carrier transfer process. I think it's a bit like multiple exciton generation. Works really well in very isolated systems. It's like a tuning fork. So if the energies are resonant, they match. Like, can actually use de Broglie's wave picture to show like basically higher harmonics and they couple, etc.
Yeah.
And that, for instance, that works in like lead selenide, lead sulfide core shell dots in colloidals, because they're all isolated systems. But as soon as you got a wave function overlap, so your overlap integral is bigger than 0, that means if you have a charge transfer from your layer into the silicon, then all these decaying wave functions from the silicon will influence your spin configuration in your organic.
Yeah.
That makes it like mutually prohibitive. So either you have good coupling, but your Singlet Fission doesn't take place because of that coupling, or you have very nice Singlet Fission, but then you can't really transfer the carriers because you have a major barrier, which is actually required to keep this spin configuration intact. So it's kind of mutually exclusive.
Well, yes, that's why I think you'll have to have an interlayer to sort of scramble the triplet spin before you put it into silicon. Yeah.
Okay. Well, we're going to pack up, so we'll finish there. Let's thank Murad again for that very interesting talk.